So I think we can get started now. So hello all and welcome to the latest seminar of our Scientific Machine Learning seminar series. And today it's my great pleasure to welcome Pan Du to give us a talk on his research. So Pan received his bachelor's degree in thermal engineering from Tsinghua University and completed his master's in mechanical engineering at Washington University in St. Louis. He is currently a Ph.D. candidate in Aerospace and Mechanical Engineering at the University of Notre Dame under the guidance of Professor Jian-Xun Wang. Pan's research spans multiple disciplines, including scientific machine learning, Bayesian inference, uncertainty quantification, geometric deep learning, and computational fluid mechanics. It's a great pleasure to have you here today, and please feel free to take it away. Yeah.
Yeah, thank you very much for the introduction. Hey guys, it's a great honor for me to present my latest research about turbulence generation using conditional neural field latent diffusion model with four-step stochastic spatiotemporal turbulence. I'm currently a PhD student at the University of Notre Dame, and this work is a collaborative work between me and my lab mates under the guidance of Professor Wang. So to give a little bit of background, in fluid mechanics, eddy-resolving turbulence simulations, such as direct numerical simulations, LES, are very important to predict complex unsteady behaviors of turbulence flow. And this is fundamental to various engineering and scientific applications. However, first, traditionally, those solvers are very time-consuming to compute, majorly because those simulations typically have very high spatial and temporal resolution. This is kind of a gallery of all the turbulence flows we have computed in our group, and this is done by a differentiable solver based on the inverse boundary method. It's called the diff flow FSI. We have a couple of publications upon this, and you can search this name for further information. So there has been methods in this community to leverage AI technologies to accelerate the computation of turbulence flow. And I'm just gonna give a little bit of introduction of what people have done upon this topic. So earlier attempts of this AI application for turbulence acceleration involves using a encoder, a decoder architecture, and typically accompanied by a neural network model to learn the temporal coherence between the previous time step and the next one. For example, Fukami in 2019 has used a convolutional neural network as an encoder and decoder, and directly use a multi-layer perceptron network, which is a very simple architecture to learn the temporal dynamics of turbulence on regular grid. And later work have done this same architecture, but switching the temporal learning component from an MLP to a more updated version, which is a recurrent neural network. And a previous work in our group has extended this application into unstructured grid. And if you use an unstructured grid, you need to handle the unstructured mesh. That's why we switched the encoder into a graph neural network. And for the temporal learning, we used a transformer to learn the temporal correlation between the previous step and the next step. And the more recent work in our group has been using hybrid neural solvers. That's kind of combining the solver and the neural network together to ensure the solver accuracy as well as the efficiency. To overview the previous methods, we can identify that they typically use a architecture where we have to use a neural network-based encoder to compress those large-scale turbulence data into latent space. And then we will use a recurrent neural network to learn from the previous latent encoding to the next one. And this recurrent neural network, once learned, are typically using to predict the temporal dynamics in an autoregressive way, meaning that given an initial time step, you can apply it multiple times to predict the forward flow field step by step. And also a very big important characteristic of those methods is that they are typically using a supervised learning approach, meaning that typically all those training data are computed from numerical solvers, and we use that data as the training data for the neural network model. And this approach can achieve very good results. And this is typically a very typical, machine learning results versus the ground truth. You can see that the prediction, which is highlighted by the red curve, is pretty close to the ground truth. But you can also see that because it is using an autoregressive approach, the prediction error can accumulate, and the prediction results can start to deviate from the ground truth as time going forward. And those supervised learning surrogate models has another disadvantage, is that turbulence in nature is inherently a stochastic and chaotic system. So if you start from a starting flow field, it can evolve into multiple realizations because there are inherent randomness in those turbulence flows. However, for those supervised surrogate models in previous work, they can only predict one of them. And that's the first point. The deterministic model can, at best, produce one particular realization, but cannot generalize other possible realizations under the same probability density distribution of the turbulence system. And another point about turbulence is that it has a chaotic nature, which means even a slightly fluctuation in the flow field can be magnified as time going forwards and develop into totally different flow fields. And because of that, most of the supervised surrogate models in the previous work can encounter, encounter unconvergence or simply exploding when they do the inference. And here are some examples where you can see that the prediction goes pretty well for the first few time seconds, and then it will start to either deviate from the ground truth or just explode in certain part of the flow fields. And another question we might ask is that, okay, since it's pretty difficult to learn this chaotic system, how about we just learn a flow that match the statistics of the flow field? In turbulence, we typically use like first order and second order statistics, such as flow mean profile of the UVW exponents or the pressure. That's the first order metrics. For the second order metrics, this would typically be the fluctuation in different directions of the velocity and the pressure. And if you do that, you can see that even if you learn a flow using the machine learning way, which you can see on the right-hand side, this is the result. And compared to the DNS, they have the same first order statistics. However, they are totally different in terms of flow structures and coherent turbulence flow patterns. So since a turbulence is a stochastic and chaotic system, it can be described as a probability density function. And we propose a new way to learn the underlying PDF of this stochastic system. And typically, turbulence flow is in 4D space-time, meaning 3D in space and 1D in time. And it has an extremely high dimension. They usually use very high resolution grid and time discretization, This will result in a very complex probability landscape. And we are using generative AI technologies to learn the underlying probability distribution. And we have been published some papers on this approach. You can check all those references in our group. And all those models are aiming for generating spatial-temporal instantaneous turbulence using generative AI technology. For example, we have been previously using a graph encoder-decoder architecture accompanied by a transformer to learn the spatial-temporal dynamics of turbulence. You can see that those different realizations of this backward step flow, it has different flow field, of course, but they all are one realization of this probability distribution. And if you plot out the metrics, for example, this is the turbulence spectrum, you can see that it aligns with the ground truth very well. You can look at our results as the red curve, and the ground truth is the LES simulation. And if you plot out the probability distribution at typical locations in your flow field, you can see that prediction and the ground truth aligns generally in a decent. However, this model is using a normalized flow-based probabilistic model to learn the distribution. However, as you may know, normalizing flows typically have to compute the Jacobian matrices, which is very time and memory consuming. And because of that, those kind of models cannot be scalable to even higher large-scale turbulence flows. And we have been trying to use more memory-efficient generative AI models. And that's why we have published a paper in our group for turbulence flow generation using diffusion model. And if you look at the diffusion model, people typically refer to diffusion model as you add noise to the data and you disturb it into white noise. And you use a neural network to learn the reverse process where you first of all, you generate a random noise data, and then you use the neural network to autoaggressively denoise it into a clear data, which aligns very well with the underlying probability distribution. And this is a schematic of the flow field going from a very clear stage into a noisy stage and going back to generate synthesized turbulence flows. And this paper is published in CME. However, this paper does not have a very efficient encoder and cannot handle irregular domains such as irregular shapes of the boundary of the computational domain or unstructured mesh. And for our latest iteration of this approach, we propose a model called CoNFiLD. The full name is Conditional Neural Field Latent Diffusion for Space-Time Turbulence Generation. And in this architecture, we use the conditional neural field as the encoder. A very big advantage of this conditional neural field technology is that it implicitly represents the turbulence flow field using a neural network. And because of that, it can support irregular domain and unstructured mesh. And also, it typically has a larger compression ratio when compared to conventional dimension reduction tools such as Ph.D.s or convolutional autoencoders. And after we encode those turbulence flows into latent vectors, we actually can use the latent vectors as the training sample for the diffusion model. And in this way, diffusion model will learn the data distribution in the latent space, which is very memory efficient. And after the diffusion is learned, we can generate noisy image and denoise them into clear image of the latent data. And then we use the CNF decoder to decode back into the physical space and generate synthesized turbulence flow. And this is an example of the generated flow for turbulence inlet. This is typically an inlet snapshot or cross-sectional view of a 3D turbulence channel flow. And you can see different realizations. They are different from each other, but they look similar and preserves the turbulence structures in the animation. And this is, we further compare those realizations with the ground truth. And the ground truth is computed by the DNF method. And you can see that we also plot out the first order and second order metrics, such as the mean velocity profile, the turbulence fluctuations in the UVW direction, as well as the two-part correlations. You can see that our predicted results aligns very well with the ground truth, both for the first order and second order statistics. Furthermore, one question people may wonder is that, are those generated turbulence flows physical? And we actually put those inlet snapshots into a 3D turbulence channel flow and let it develop forward downstream so that we can check if the flow is fully developed into turbulence or not. So we use a traditional approach such as convolutional LSTM as a baseline, and it is compared with our CoNFiLD model and also compared with a DNS precursor simulation. We can see that if we check 0.6 pi downstream, we can see that the turbulence spectrum of our method, which is highlighted in the red line, is closer to the ground truth, which is the blue dots for the DNS, and outperforms the SOTA method comes from the convolutional LSTM. If we check further downstream, we can see that our model fully develops into a physical turbulence field, and the SOTA method kind of under-predicting all the high spectrum turbulence structures. Then we also extend our CoNFiLD generation into a regular grid. So this is a turbulence flow over a periodic Hill domain. And it is a 3D simulation, but we use a span-wise cross-sectional data to learn the spatiotemporal turbulence flows. And here I'm just showing 3 of the random realizations generated by CoNFiLD compared to the ground truth. And you may guess which one is the ground truth and which one is the generated realizations. And the fact is that you cannot actually tell them because they are very similar to each other, but still different. And they are preserving the same turbulence inherent flow structures. Actually, the first one is the DN simulation, and the bottom 3 are the random realizations. And you can see that there is very physical flow separations and large turbulence structures going on in the middle channel of the domain. And all those visualization results kind of support that our CoNFiLD generation can actually estimate turbulence in a very physical and efficient way. And we also plotted out the velocity metrics as well as the spectrum for this periodic Hill case. And we can see that for the ground truth, which is highlighted in a scatter plot in blue, and our model prediction are very close to the ground truth. And we extend our case even to a more large-scale turbulence simulation, which is a one-bounded turbulence with ruffle settings. So as you can see, we have visualizations of the volumetric rendering and the cross-sectional velocity magnitude, as well as a vortex animation. You can see that those DNS simulation is different from the CoNFiLD generated flows. However, the CoNFiLD generated flows preserves similar turbulence in coherent structures as the ground truth. And if you plot out the velocity mean and fluctuations in the flow field, you can see on the left side that our prediction and the ground truth aligns very well. And we also want to discuss the computational cost and memory usage of CoNFiLD. The left figure shows that traditionally we actually use a numerical solver to solve turbulence. We use a OpenFOAM as the example, and we calculate the total time it will take to finish one flow through time of this turbulence channel flow. And we consecutively plot out state-of-art AI accelerated turbulence simulation method in the second, third, and fourth column. And the second one is the DiffFSI, which is our in-house GPU-enabled CFD solver based on inverse boundary method. And the third one is a very state-of-art model architecture called video diffusion, where we use that as in our previous application to generate spatial-temporal turbulence. And the last column is our CoNFiLD. As you can see that our CoNFiLD can achieve over 1,000 acceleration, and the time it used are dissected into two parts. The blue part is the encoding part, which only occupies a small part of the total time, and the major time consumed is used for computing the spatial temporal dynamics. And also we plot out the GPU memory usage plot, comparing the video diffusion model, which is state-of-art method in previous work, and compare it to our CoNFiLD. You can see that the video diffusion will quickly reaches the upper limit of industrial standard GPUs when the inference length increases. For the A100, the video diffusion actually stops at around 120 time steps. However, from our CoNFiLD, we can actually infer as many as thousands of time steps, thanks to our very efficient encoder component called the conditional neural field. And another thing we want to mention is that our CoNFiLD also features conditional generation. And this is a big advantage because you can use a specific condition and put it into the model. Our CoNFiLD can actually simulate the corresponding flow realizations that satisfy this condition. For example, you can take some measurements from a flow field, and this is the turbulence flow over rough wall. And those cylindrical objects are actually flow sensors that can measure the velocity or either pressure values. And you can use those data to reconstruct the full spatial temporal flow field. Another example is that, let's say you have some low resolution space-time data, you can actually use that to do super resolution, where it will give you, turbulence structures with higher frequency. Another application is that you can start from a very low fidelity turbulence model, for example, a flow field computed on steady rains, and you can actually use that to reconstruct more accurate and higher resolution turbulence flows in areas. And we propose this approach as Bayesian latent conditional generation. And notice that all those conditional generation scenarios does not need to retrain our model, because our model can readily be adapted to all kinds of different conditional information based without any retraining. And this is called the zero-shot deep posterior sampling, where typically we put our input condition, such as flow measurements, into the diffusion model along with the random noise, and the diffusion model will generate different realizations in the latent space, and those latent space encodings can be passed into the CNF decoder to generate physical flows that satisfy those measurements. The first example we want to show is for the periodic Hill flow case. We placed random 10 sensors into the flow field, and we actually plot out the signal measured from those flow fields into the plot in the left side. The ground truth signal is highlighted in the blue dashed line, and the measurements are highlighted in those blue circles. And you can see that as the signal going forward in time, we can actually reconstruct full spatial-temporal turbulence flow in the visualization on the bottom. Those flows are actually having a very close, flow field signals compared to the measurements. And we also show that CoNFiLD can do such conditional generation for the large-scale wrong-balding turbulence as well. So again, we place a couple of sensors in the flow field. We take the measurements, and those measurements can be used to reconstruct the whole spatial-temporal flow field using this conditional generation approach. You can see that a very unique finding is that the generated turbulence structure this time is very similar to the ground truth because those measurements kind of reduce the uncertainty of the posterior by a very large extent. And this is actually good news because our goal of this approach is to actually reconstruct the flow field that should be very close to the ground truth. And we also kind of play with the conditional information settings. For example, in this plot, you can see that we actually increased this number of sensors. We also infused some noise into the sensor measurements to test the robustness of the conditional generation of our conflict model. The first row of the figures are the probe locations. This is where the measurements are taken in the flow field. And the unprobed locations are just random points that are not located on the as the sensors. So if you look at the first sensor conditional, one sensor conditional generation, because we are using only one sensor measurements, you can see that the generated turbulence flows has a very large uncertainty in terms of the flow magnitude on this specific location, both for the probed and unprobed. And if you increase the conditional information, this will largely reduce this uncertainty. As you can see in the second column, you can see that all the measurement uncertainties kind of collapsed, and the ensemble is very thin, but it aligns with the ground truth measurements very well, both at the probed and unprobed locations. And for the third column, we added some noise for the measurements, which is highlighted in those black circles. And we can see that the generated signal is still very close to the ground truth. This demonstrates that our CoNFiLD has a certain level of robustness to noise. And this is another application for our conditional generation for CoNFiLD. This one is the super resolution, meaning that if you have a low resolution spatial temporal flow field, you can actually use that to reconstruct a higher resolution turbulence flow. And you can see that we demonstrate 3 different cases. The first column is actually 64 by 16, and the second and third are lower resolution all the way to 4 by 1. And you can see that all the generated turbulence flows actually are very similar, but the best performance happens when it is constructed from the highest 64 by 16 resolution. And this demonstrates that these conditional generation results can actually realize this super resolution task. We also plot out the turbulence spectrum, and the blue line, the blue dots are the ground truth, and the red line, solid line, with our CoNFiLD super resolution results. And we also kind of compare it to directly doing the bicubic interpolation for the super resolution task. You can see that because it is bicubic interpolation, all the high frequency turbulent structures are kind of underpredicted. However, our CoNFiLD model can actually predict very close turbulent spectrums when compared to the ground truth. And also another note for those different resolution reconstruction is that you can freely switch from one resolution to another without need to retraining the CoNFiLD model. Just to conclude, we actually introduced a conditional neural field latent diffusion model to learn the underlying probabilistic for the 4D flow turbulence. And our generative flow has first order and second order metrics matching very well with the DNS data. Also, our CoNFiLD model offers versatile zero-shot conditional generation capabilities, and those applications include sensor reconstruction, super resolution, flow restoration, and so on. Those results actually show that our CoNFiLD can be applied to real-time data assimilation and to solve a lot of inverse problems with quantified uncertainty of the turbulence flow field. And we planning to do future work to upgrade the CF encoder to make the CoNFiLD to be applicable to even larger scale turbulence data. And you can actually scan those QR codes to see further animations of our results. And you can check the paper name on arXiv as well as Nature Communication Journal to see the more details about our paper. Thank you very much. I'm happy to take any questions.
Okay, let's thank the speaker first of all. Yeah, that was a great talk, Pan, and actually we have lots of time for discussion and more in-depth questions. Could you jump back all the way to slide 7, I think, where you first introduced some of the methods such as CoNFiLD and so on?
Yep.
Yeah. So firstly, could you actually explain how you are setting up the CNF encoder and what sort of inputs do you need to feed into it, and how do you sort of compare it against other approaches for also doing neural field encoding and so on?
Yeah, that's a very good question. So for our CNF encoder, it is actually taking a point coordinate. As you can see in the figure, we have using XYZ to label the point coordinates. And these point coordinates are fed into the siren network. And this siren network is actually MLP using not the relo activation, but using the sign activation. And it will output the corresponding fluid quantities, for example, the UVW values at the corresponding location. And we also have a film conditional module. And you can consider the siren is kind of, it can implicitly represent one snapshot of the turbulence field, right? If you fit like one snapshot, you just take the siren and you take every point coordinate and the UVP as a training pair. And every point in your flow field would be one training sample, right? So you use all the training data to train one siren, and you can actually, after it is trained, you can actually put in any query points anywhere, and you can get the corresponding fluid quantities. And you can consider it as siren is actually implicitly representing this field by kind of approximating the function that maps the coordinates to the flow field. And if you want to encode multiple snapshots, you actually, in the very naive way, you can actually just, if you have like 4 snapshots, you can just use 4 different sirens, right? But in reality is that those snapshots, especially if you take very close time snapshots, those snapshots are temporally correlated, which means the functions you learned in those 4 different sirens, they're going to be pretty similar. So you do not actually need to use independent siren models to, fit all those 4 correlated snapshots. So we added a conditional module, which is called film. And this film module is pretty straightforward. It's actually using a latent vector as an input, and it will produce bias values. And those bias values will be added into the hidden layers inside the siren network. So every snapshot will be associated with one encoding, right? You can see that in the figure, you have like 4 flow snapshots, and those 4 flow snapshots actually corresponding to those 4 column colorful vectors. Those are the latent encodings. And one latent encoding is associated to one snapshot. And if you pass the latent encoding into the film, it will produce biases in the hidden layers. And this will be added into the siren network, such that it kind of only modifying partial of the learned function to fine tune it such that the modified siren will be approximating the specific realization. So this is kind of an idea in meta learning where you train the conditional neural field on multiple snapshots. The siren is kind of a averaged template for your flow field sequence. And the film is responsible for further fine tune of this meta model so that you can actually fit whatever snapshot you want to fit using a kind of a specialized encoding, right? Yeah.
And then when you are feeding in these values of the flow field at different coordinates into Siren, I imagine that you don't necessarily need to feed in the full snapshot, but you could just randomly sample points, or do you sort of just take in all the data that's available to train Siren typically?
Yeah, that's a pretty good question. So actually, in all our training cases, we kind of downsample it first because typically our training data set, our original simulated results is in very, very high resolution. And those high resolution are, well, if you have those high resolution, it is good because high resolution means that you can capture even the finest turbulent structures in the flow film, right? But those data scale is too much for the CF encoder. So we will typically downsample, but in a uniform way. I'll take one very simple example is that for the turbulence flow inlet, we will actually probably have like 512 by 512 resolution for the regular grid, but we will downsample into, let's say, 400 by 100 so that we will reduce the dataset size. But it is not supposed to be a operation that you want to do, but it's more like you want to save memory and make the training process feasible to the GPU you have. So typically, this downsample process is needed for the signal. Yeah.
Okay. And then when you are actually generating this rollout, like how does that decoding process really works. So you get these latent encodings for each of these four snapshots, and then
Yeah.
does it just pass through the CNF decoder and that's supposed to, so is it just purely, is that decoder then just purely reconstructing these, or then do you also have some sort of rollout that's happening over here?
Yeah. So this is actually related to a major difference between our concept model and previous models. So as I mentioned before, for the previous work, they typically use like a one-step surrogate model, right? You use an MLP to learn from the previous latent vector to the next one. And if you do that in the inference stage, you will have to apply this one-step predictor again and again in an autoregressive way to predict a very long time sequence. But that's not the case for our CoNFiLD model. As you can see that in the left corner of our model diagram, the four flow snapshots are encoded into four column vectors, right? Those four column vectors can be put together into an image, 2D image, where the vertical dimension represents the number of latent vectors, the number of elements in the latent vectors, and the horizontal dimension represents the number of time steps. And this image will be served as the training data for the diffusion model. So when the diffusion model is generating a latent image, you can actually split it into different columns. And these different columns can be individually decoded back into the physical space, which means that the diffusion model is actually doing the temporal prediction for you, right? Inherently just capture the temperature correlation in one prediction step. And another a very unique feature of this technique is that the diffusion model is typically using a UNet CNN UNet structure to learn the denoising. And this UNet structure is not requiring a fixed dimension for the input data. For example, if your training data is like 8 by 8 images for your CNN unit, when you do the inference, you can actually put in other dimension of image. You can put in like 16 by, you can put in like 8 by 16. You can put in 8 by 100. Because those are all compatible with the convolutional kernels inside the same unit, right? So this means that if you, so our CoNFiLD is actually training on like different time period of, turbulence flows with a fixed time interval, right? So if you, let's say you just train it on like 100 time steps, but in the generation process, we can actually generating very long time sequences, which can be much higher than your training length. And you can do this by, you can realize this by just simply generate a very long noisy image first and put it into the diffusion model, into a decode back into a latent image. And you can just split them into very long sequence of vectors and transfer them back into the physical space. So actually, that's why in the diagram, you can see that the generated physical flow actually have more, time steps than the training data set. Yeah.
Yeah, that's actually pretty nice.
Mhm.
One last question before I hand it off to other people.
Yeah.
You go all the way to slide 16.
16.
Yes.
Sure.
Yeah.
Yes.
So
Mhm.
one of the things I was wondering was, do you have any intuition or process by which you select the locations for where to place the sensors? Because I imagine that even in like the 100 sensor case, you could be placing sensors in the domain such that you have two sensors that are like really close by, but the flow field in that region is pretty well correlated anyways. So that second sensor could have been better off placed somewhere else in the domain where maybe there is like more information to be gained. So do you sort of also design the sensor locations when you do these cases?
Yeah, that's a very, very good question. For the case you see in this slide, we actually just randomly placed the sensor location for demonstration. But what you're saying is true. For example, in this periodic kill case, in some locations, the sensor information are kind of not that much informative. So such that if you use it as the conditional information, right? The uncertainty of your generated ensemble is not going to be reduced, right? But comparing to that, you just place the sensor into, for example, the near wall locations, where it will clearly reflect any, spectral, like flow separations, those kind of stuff. Those kind of sensors are distinctly reflecting what is going on in this specific flow randomization, right? So if you use more of those points as conditional information, actually you can reduce the uncertainty by a very large extent, even if you use a very few of them. So, I think in practice, you can actually smartly choose those locations such that you can use a minimum number of those sensor locations to, reduce this uncertainty that is small enough to consider it as a reconstruction of the flow field, right? So for those, but for the strategy of the selecting the locations, I would recommend that one need to observe the flow field first and identify which part or which location in the flow field has distinct flag vortex flow pattern changes going on, which will have a very unique signal reflecting this flow involvement. And I will typically choose those locations for the conditional locations, especially for sensor reconstruction tasks.
Yeah, thank you. I'll hand it off to other people in the room as well
Yeah.
as on. Yeah.
Yeah, I have one question. So I'm interested in if you could speak a little bit to the kind of generalizability or extrapolation capabilities of this sort of model, and like in what sort of scenarios would you need to redo the DNS and retrain your model versus what scenarios could your model that you've already trained be applied to already?
Yeah, actually, it depends on the data set. So we have actually demonstrate that for example, this turbulence inlet flow case, right? So for this turbulent inlet flow case, this is actually the snapshot of the inlet of the turbulence channel flow. And this is what we call a stationary turbulence, meaning that if you calculate the velocity mean, like in the time direction, of course, the velocity mean is actually fixed, right? So if you have this fixed flow means, it means that this specific simulation data has a limited space of variations. And if you learn CoNFiLD on those kind of stationary turbulence, statistically stationary turbulence, it can actually capture the space very well. So it will actually generalize to, it will have a very, very good generalized capability. For example, you can just use your software to run individual turbulence channel flow and take the snapshot again, which is a new data. and you take some measurements, the CoNFiLD can reconstruct your simulation very well. And all those cases we provided here actually can be classified into statistically stationary turbulence. So what you mentioned for the generalizability, for example, in other scenarios, such as statistically not stationary turbulence, where you have to kind of use, for example, use like an auxiliary lens to capture the flow means. In those scenarios, our CoNFiLD cannot generalize to that, and this is one major limitation of our CoNFiLD model. And we do have plans to improve the generalizability of those kind of scenarios. We can actually do it by, combining CoNFiLD with some kind of low fidelity solvers, because as you know, solvers, while they're very time consuming, they can actually generalize to a lot of cases. But we can only do the solving part in a very low fidelity settings, and we can just fill up all the finer structures using our CoNFiLD model. So if we do this kind of hybrid approach, we can actually improve the generalizability of the CoNFiLD model for those statistically non-stationary turbulence. And also, for example, another generalization case is that you may wonder, can you generalize to different, boundaries? For example, if you have like this wall bounding turbulence settings, and you want to change the size of those cubes, or even change the shape of it. And currently, I think, well, theoretically, CoNFiLD model can definitely do that, only by including a set of variations in the shape and sizes, and you have to compute the turbulent simulation for those configurations, and include all those computed flow simulations into your training data. And if you do that, CoNFiLD can actually generalize to different type of boundary shape and sizes for you. But that would be very memory and data intensive in those kind of generalizations now. Yeah.
I see. Okay, thank you.
Yeah.
Other questions for Pan? Okay, if not, we can wrap up a little early. Let's thank the speaker again for this wonderful talk. Yeah, and yeah, thanks, Pan. Nice hearing from you, and very cool animations. And
Yeah.
yeah.
Yep. Thank you very much.